So the second question, we have a point charge of 15 microcoulombs is placed at the point n2 minus 36 and a uniform line charge density of 120 microcoulombs per meter lies along y-axis. Find I, the electric flux density at point B, where the coordinates are 2 minus 3, 6. And then I, the total electric flux leaving the surface of the sphere of 3 meters radius centered at the origin. Then B, a sphere of radius r in figure 1 has a uniform volume charge density. Find the electric field at point outside the sphere and at point inside the sphere. Okay. So this is the question. Now let's start with 2a. We have to find the electric field intensity at point B, meaning I. So to get this, we have question. So if we are to find the electric flux density at point B, right? So what that means is that the electric flux density is going to be equals to, at point B will be equals to the electric flux density due to the charge which is placed at the origin, right? Plus the electric field intensity due to the line charge, right? So due to the line charge that we have, which is located at the y-axis. So this is how we go about solving this. We solve this based on what the principle of superposition. Now let's get the electric field intensity. Okay, is the point. No, the other one is located at n, not origin. So it's located at n, it's not the origin. So, but here the coordinate is 2. Okay. Okay, here it was corrected, later corrected to be at the origin. I corrected this because you can see that point n and then point B are having the same coordinates, so it doesn't make sense. So it was rather corrected to be at the origin. So we are solving this. Now the electric field intensity at the origin is going to be equals to, meaning the charge, right, which is placed at the origin. So this one, the charge which is placed at the origin, then over 4 pi, right, r square, then times the unit vector, right? This is for the electric flux density due to the charge placed at the origin. Then we get the electric flux density due to the line charge, right? So when it comes to line charge, we know this is going to be equals to the line charge density over 2 pi r, then we have AR, right? So this is the equations that we have. So let's start with the first one. So to get this one first, you can see that we have to find R, right? And R here is simply going to be the distance between the charge which is placed at the origin. So meaning if we have our charge here, it's at the origin, so that means the coordinates are 0, 0. And then we have a point B. And the coordinates of point B are, when it comes to point B, the coordinates, what are we giving? We are giving 2 minus 3, 6. So we have 2 minus 3, 6. 2 minus 3, 6. Okay, So these are the questions. So we have to find here the distance, which is going to be what our, we can call it RB, right? You can call it RB. It's labeling. So to find RB is going to be equals to taking the square root of what, meaning point B minus the origin. So we have here 2 minus 0, that will just be what, 2 square plus minus 3 square plus 6 square. So what do we get? So we get 4 plus 9 plus 6 square minus square root 49, which is what, 7, right? So this becomes 7 square root of 40 is 7. Okay, so we get 7 here. It's to be 7. Now I'm done with this. Now let's get R here. So when you come to the line charge density, when you can talk about R is again is going to also be the distance between our point B and then the location of what the line charge density that we have. So you can see that it's at the what, the Y is located on the what, Y axis. So when it comes to this, since it's located in Y axis, what that means is that the coordinates, the electric flux density component of that is going to what, that Y is going to cancel out, right? So that means that the coordinates, the component of what, the electric flux density in the where the infinite line charge is lying is going to be 0. So as a result, we write R will be equals to, just meaning since we are in the Y, is our line charge is lying in the Y axis, so we neglect that. So that one we neglect this. So meaning my B in a nutshell probably is now, we have to, then I have 6, right? So I have here 2 square plus 6 square. So meaning we have here 4 plus 6 square, that will be 40, root 40. We have this. Okay. Now that we've done this, but we have to get the what? This is the magnitude of our distance, We have to get the vector R here will be equals to, we neglect the Y component, so I'll just have 2 along the X axis plus 6 along the Z axis. So we have that. Now with this being done, we can just come and replace our values, right? This will now be equals to the charge which is given from the question, right? The charge is giving us, I have to go back, so I'll get the charge. Remember the question. The charge is giving us 15 microcoulombs, and then the line charge is 120. So I can write 15 microcoulombs. 15 microcoulombs, then over 4 times pi times R square. Our R is what? Okay. Now that we've done this, it's also important, we have to talk about the unit vector, right? ARB. And this unit vector, ARB, is going to be equal to what? Right, the vector over its magnitude. So it's going to be, the vector here is going to be 2AS minus 3AY plus 6 along the Z axis over its magnitude, which is 7, right? So we get this to be 7. So here I can have another 7 here. Then we have it again 2 along the x-axis, right? Then we have -3 along the y-axis, plus 6 along the z-axis. So we have this here. Then I can add my line charge density, which is here with plus 120 over 2 pi times our r. This time, remember r here, we got root 40. And again, this one, we have to get the unit vector, right? The unit vector. So this one, r will be equals to me the vector r over its magnitude. So the vector r is what, 2 plus 6 along the z over its magnitude, which is what, root 40. So now that we've done this, the electric flux density at point B will now be equals to, here we have 15 raised to the power 3 times 3.32 -4 along the x-axis, 3 along the y-axis plus 6 along the x-axis. So we got this one here. Now that we have this, then we bring this one to here. I have 2 times pi times, but this one, that would just be 40. So times 40 inverse times 120. So we have here 0.477. So we have 0.477. Now that we have this, so we bring our brackets to along the x-axis plus 6 along the y-axis. So we have this. Now I'm going to now get this. So let's start with this 3.32 times 2. Okay, let me try and get this one again. 4 times pi times 7 over 3 inverse times 1/5. Okay. Now it's 3.48. Yes, with 3.48. So times to the power 3 times 2. So here we get here to be 6.96. Okay, 6.96 here. Then here we know minus. So when you multiply this by 3, you get 10.44 along the y-axis, and the last one you get 20.88 along the z-axis, right? And then now you put all of them into bracket milli, because we have 10 raised to the power 3 here. So we get this millivolts per meters. So we get this. Okay, we have to do, I'm doing all of them at a time, so I'll just do it this way. We are doing this all of them at a time, so I can write times 10 to the power minus 3 here. So let's come and do the other one. So we have here plus 0.477 times 2. That is 0.954. Then here plus 0.477 times 6, 2.862. So we have this here. Okay. Yeah. So we have this. Let me see this again. If I'm correct, let me do this one. 2 times pi times 40 inverse times 120. Yeah, so we get this. So our answers are now going to be, remember here is what, so we just add, this one will remain the same, 10.44, right? So here I'll just add 6.96 plus 0. No. So you have to multiply times 10 to the power minus 3 plus 0.954. Right, you get 0.996 along the x-axis, and then this one we get 20.88 times 10 to the power minus 3. Okay, 120 here. Oh, okay. I've forgotten the 10 raised to the power, listen, 6. And then even with the 120, we have here we have 15 micro and 120 micro. I didn't take those into consideration. Yeah. So here we want here. So here I didn't take this into times 10 to the power minus 6 here, right? So meaning this one with times 10 to the power. So here with 10 to the power minus 9. This will be minus 9. Wow. Yeah, it should be minus 9. And then here we want meaning 0 point, meaning this times 10 raised power. Okay, let me put here should be 10 raised to the power minus 6. Here is 9. Okay. So here this will change. So now if we have here to be 6.96 times 10 to the power minus 9 plus, let me just, this plus 0 point 0.954 times 10 to the power minus 6. Okay, 9.7. 9.6. This is now milli will be what? 0.96 milli. 0.96. A micro rather, right? 0.96 micro. Okay, I know here will be micro, so let me put this outside. Okay, so but this one is nano. Yeah. So it's 10 raised to the power minus 6. Okay, so let's do the other one. 20.88 times 10 to the power minus 9 plus into bracket 2.862 times 10 to the power minus 6. So if we make here to be, meaning here will be nano. So this one will be 10 raised to the power, meaning 10 times 10.44 times 10 to the power minus 3. 0 point. So here we make here to be 0.01. Then we put the whole of this to be micro. Remember, this is what electric flash. Okay, so we are still on this question. The electric flux density at point B. So here I think I'm expressing everything in micro, but let's do it in nano. Right? Think in nano. So from here, and to express this in terms of nano rather, I think nano will be much simpler. So if we are doing this in nano, from here, this very part, remember here 10 raised to the power minus 6 So here there has to be 10 raised to the power minus 6 here, right? So imagine all this is in nano. So for it to also be in nano here, that means I'm rather going to what? Make this in 4. So we can now write this to be in terms of milli. That would 10 raised to the power 10 raised to the power minus 6. So I can write 477 times 10 raised to the power minus 3 times 10 raised to the power minus 6. So that would just be 10 raised to the power minus 9 here. Okay, make this one 9. So that when we come here, then I'll just take here, let's erase this, so that we get something of the sort. I'll get 2 times 477. That'll be 94 along the x-axis. Then I have the next one is what? 477 times 6 to what? 2862 along the z-axis. So I have this here will be 10 raised to the power minus 9. Okay, so that's the term. So we have something of this nature. So I can now, so you can see all of them are 10 raised to the power minus 9. That is nano. So I can just now expand on and add them. So I can just add this and this, and then add the latter one. So let's do that. So I can get here 6.96 times a plus 954. That would be 960. Along the x-axis. We have minus this one just remain the same, 10.44. Okay. Then here will now be 20.88 plus 2862. 288 along the axis. So we have this, and all this in what? Nano coulombs per meter square. This electric flux density. So we get this along the line. Now, so with this we move to the next question, which is question B. So question B, we are given a sphere of radius r in figure 1 has a uniform volume charge density. Find the electric field at point outside the sphere and at the point inside the sphere. So what that means that with our, if you go to, it's not here, but it's like this. The figure is given is somewhere of this nature. We have this, then we have a volume charge density. So we have a sphere, and that sphere meaning we have some charges inside, right? So that's why we have, in that case, volume charge density. And then we have to find the electric field intensity, right? If we have what r is outside, which is our, the radius here means that radius is going to be considered to our Gaussian radius, right? So let's say here from here to here, from the question, we have A, right? This is A, and then outside, meaning here I have R. Okay. So first we start with what? So let's say we place a point P outside of our